Really beautiful introduction prepared for Nirmal, but he blew it. So he's going to tell us about new physics anticipations in LHC dilepton angle.
We like you anyway.
Thank you. Apologies anyway. So thanks for having me over here at Davis, which I found to my pleasant surprise is actually just down the road from where I work, as you can see in the Google Maps instructions. So
30 hours on IT.
Yeah. Just 3 instructions, yeah. So today I just wanted to talk about a really fun project that I finished up last month, which is to put more focus on angular spectra. Okay, or to elevate the consequence of angular spectra to a discovery. Okay, so let's begin. Okay, so for better or worse, the second run of LHC is upon us, pretty much defining our energy frontier now. And this is how the energy frontier looks. Right? These are the inclusive production cross sections of every species in the standard model. And I would like to focus your attention on the very left edge of this plot, which is the inclusive production of the vector bosons of the standard model. And in particular, the features of these processes are, yeah, you had a question?
No.
Okay,
sorry, I'm just trying to read your, go ahead, it's nothing to do.
Okay. So these processes in particular have very high rates and correspondingly small uncertainties, which makes them an ideal testing ground for the standard model, or conversely to look for new physics, if you want to go from bottom-up approach, right? And in particular, we are going to focus on the exclusive channel of dilepton production, which is the Drell-Yan process here, which is nothing but QQ bar in the initial state with L plus L minus in the final state. That is touted to be the largest Feynman diagram on Earth, embossed on the atrium floor of University of Oregon. And this was commissioned in 1976, I believe. So this process has been around for a long time, and it has given us a lot of historic successes. Why do we love this process? Once again, it has high rates, gives you some of the it gives you a very clean final state in any collider environment. It has very well understood backgrounds, so improving the significance of new particles. And so CMS, one of the first things CMS did was to go rediscover all these Nobel Prize winning particles. Right?
Does it have any background? I thought it was the biggest diagram in the world.
Sorry?
Does it have any background? I thought it's the biggest diagram there is, as you said, right?
Yeah.
So it doesn't have any background.
Well, the background predominantly comes from, that vector boson. So, okay. Now the question is, we know the virtues of this channel. Can this do one more trick for us in the second run of the LHC? Okay. If so, what can we expect to? What kinds of signals can we expect to see in this channel? It's useful to organize our thoughts. It's useful to organize our anticipations in this channel, right? Well, the simplest thing that we always look for are resonances. In this case, the poster child for this is a Z prime boson. And this scenario is very well motivated because from the theoretical side, simplest extensions of the standard model can give you a Z prime, right? A U1 prime for instance. And from the experimental side also, it is very well motivated because the location of the peak in the invariant mass spectrum gives you distinctly what the mass of the particle is. And if we are lucky and able to resolve the resonance, the size of the resonance, we should be also able to extract the decay path. Right? But, and of course, this is the status of resonance searches at the latest run of the LHC, depending on what model you're looking But if you are not able to pump in enough energy to access the particle of that represents new physics, you could still look for deviations in the spectrum by characterizing new physics as contact operators, right? And so Atlas and CMS do a contact operator search and set bounds on the various combinations of contact operators that you can write down interfering with the standard model. And the virtue of this is that you can probe very high scales without having to access those scales dynamically. And this approach is great until it doesn't work. And by it doesn't work, I mean when the momentum that you put into the process is comparable to the mass of the particle, mass of the scale that you're actually probing, setting bounds this way doesn't actually make sense. And also, if new physics were such that it induces a combination of these operators instead of just one of them, then recasting them is recasting these bounds is unclear. Okay. Another pretty cool thing that you could find in this channel is deviations in the running of the electroweak couplings, right? If there was some new particle charge under the electroweak gauge that you were not able to produce just because you don't have enough rates, they may nevertheless produce deviations in the running of the coupling above the mass scale, which can be picked up in this process just because we have so much accuracy, right? So these authors tried to look at the sensitivity of this scenario using the Drell-Yan process, and they were able to set some bounds on how much deviation we can produce in the running. Okay. One more thing outside of all this that you could try to probe for are the effects of radiative corrections of a hidden sector, for instance, on the right? If you're not able to actually produce them and get enough significance to see them, you may nevertheless probe them indirectly this way. And a couple of years back, along with my advisor and some collaborators, I tried to look for spectral features that may be produced from a simplified dark matter model that has interactions with both quarks and leptons through dimension 4 interactions. And the upshot of all that was that if you compare the constraints that you can get from these deviations, there is always some parameter space where these indirect constraints do better than, say, direct detection or jet specimen searches for dark matter. Okay, so this is a laundry list of a few things that we may anticipate in the dilepton spectrum in the upcoming time. Now, in this laundry list, my attention was naturally focused on kinematic spectra, because when we think of new physics, we immediately look for deviations in the invariant mass spectrum or the PT spectrum, etc., etc. But the specialty of this channel is that you can, first of all, it's a two-body process, so it's a simple process, and all the final states are visible, and you can measure the charge of the final state. So that means, to a very good extent, you can reconstruct the scattering angle of this process. Doesn't always happen with other processes. And so you could ask then, can you have models of new physics that can debut, or just could if you can even get a 5 sigma discovery, 5 sigma significance in the angular spectra first, instead of the kinematic spectra that we do.
I think, isn't it true that for the contact operators, they use both? They use
yes.
They do use angular distributions as well as energy dependent.
Yeah, absolutely right. Yeah. That's why I phrased my question as debut. It's not clear that with contact operators you will first see it. Okay. So the angular spectra have been measured by Atlas and CMS, and yeah, again, it's the same question. Can you actually start seeing enough deviations in these spectra first? Okay. Well, we actually have a historic precedent for this. The Z prime, I don't know how many of you know this, but the Z prime was actually first glimpsed in the angular spectra before we found it as a roughness.
The Z?
No, I'm sorry, the Z boson. It's not the Z prime, the Z boson. In the late 1970s and the early 80s, we already saw a forward-backward asymmetry because of the Z gamma interference. And so we knew that there was some new physics coming up, even when we were colliding electrons in this case at 30 to 40 GeV. Right? And from that, from carefully looking at the shape of the forward-backward asymmetry spectrum, I'll tell you in a moment what that exactly means. It's a way of characterizing the angular spectra. By looking at those shapes, people were able to derive a very good bound on the Z boson, which is 100 GeV. And then the SPS was commissioned, and Rubaya, I think, was the one to suggest colliding PV bar and go discover the Z boson first. And that's what they did, and they were able to set a very good, they were able to pin down the mass very well. Okay? And then after the Z was discovered, once again they came back to angular spectra at various colliders, and were able to do precision physics, and were able to completely confirm that it was a spin 1 particle with the chiral coupling spectra, the Shannon model, etc.
Was the bound really 100 GeV? That was literally the bound?
Yeah. Yeah, I'm not making this
easy to remember.
Yeah. Yeah, I got this from an essay written by some experimentalists in the 80s. Yeah. Oops.
Oh dear.
Okay.
You just talked too long.
Right. Okay. Now, I use this phrase, forward-backward asymmetry, which is a neat way of characterizing angular spectra. And we're going to keep coming back to this concept. So let's understand completely what I exactly mean by that. Okay. So let's take this process, E plus E minus going to L plus L minus in the Shannon model. Yeah, going to some Dilepton finite state in the Shannon model. When I look at the angular spectrum, in this case the cos theta spectrum of the L plus L minus finite state, normalized appropriately. When I look at it at a very small invariant mass, where the Z boson physics has not yet kicked in, mostly mediated by the photon, then the angular spectrum is a symmetric parabola, right? And so the forward-backward asymmetry here is the area under the curve on that side minus the area under the curve on this side, normalized appropriately. And that turns out to be 0. Okay? But as we increase the energy of the process, it starts becoming asymmetric because the Z gamma interference starts kicking in. And as you can see, the forward events are fewer than the backward events, and that shows up as a negative forward-backward asymmetry. And as we get closer to the Z, again the weird interference effects start moving around, and it looks a little bit symmetric again. The forward-backward asymmetry comes back to 0. And finally, as we go far above the Z peak, it's all, the angular spectrum is dictated entirely by the Z boson. And so you get, it freezes out to a certain value for the Shannon model. Okay.
The angle is measured relative to the quark, right?
Right.
So
It's
have
not
to
the
tell us
opening.
how you get it, it's going to be tougher
At the LHC. And that's what I'm going to talk about from the next slide. So here, you knew where the E minus was coming from and the E plus was coming from. And so you were able to define a beam axis and then look at where the L minus is. And so you know exactly what the angle is. But you don't have that luxury at a PP collider, because you don't know where the quark came from and the anti-quark came from at a PP collider, which at the least it has a sign ambiguity, the angle. right? Scattering angle. But that's not all. There are more subtleties. The first one is, as I mentioned, you don't know where the Q and the Q are came from, so you don't know how to define your theta first. But there's also some transverse momentum component to the quark, so there's an ambiguity in defining what your beam axis is first. You also have ISR and FSR effects, which makes the measurement of your invariant mass challenging, for example. And there's always detector resolution issues. But luckily, it turns out, at high invariant masses, where new physics is expected, some of these effects become negligible, especially if you integrate a lot of events into large events. Okay. Also, to address these two challenges, the ambiguity in the quark direction and the ambiguity in the transverse momentum, way back in 1977, Collins and Dave Sober devised a method to define some sort of a scattering angle, which basically makes use of the fact that in the L plus L minus, you actually know where the L plus L minus 2 is. You can very well measure the 4 vectors of those, which means you can boost longitudinally until you find the dilepton center of momentum. And then what you assume is that the direction in which you boosted was the direction in which the quark came from. That is encapsulated in this ratio. The sign of PZ is put into the scattering angle definition. And with that, you are able to reduce a lot of ambiguity. So you have some definition of the scattering angle. Okay? And if this expression looks a little complicated, there is a simple way to visualize it. If you take this axis as the eta axis, and you look at where the lepton falls as opposed to the antilepton, and complete the eta axis, right? Sorry, complete the direction in both symmetrically. All you have to do is see where the antilepton falls. If the antilepton falls within this region, that is a forward event. If it falls outside that region, that is a backward event. That's all this whole definition of the Collins-Sober prescription translates to. Okay? And this may look familiar to those of us who worked on the TT bar forward backward asymmetry, because this is nothing but the charge asymmetry that is measured at the LFC for TT bar. It's just called the forward backward asymmetry, but in the limit where you can neglect the transverse momentum of the initial state partons, it is nothing but the charge asymmetry. So that gives us a very clean definition of characterizing angular distributions. Okay.
Could you?
Yeah.
How much better would you do if you? I mean, you wouldn't be hard to find to define a likelihood, right? Somehow based on the PDFs, right? Because you know. I mean, I guess you don't. Depends on the model which PDFs.
Yep.
I don't know. Can you do better by doing that? There might be some events that would be very, very rare, and
right,
you know,
right.
You should weight those more.
Yeah. So, I see.
Or
what you mean.
where I should say not rare, but where you're really sure it couldn't have come the other way. Whereas in some events it's kind of more 50-50. It's 65-45.
Right. So the probability that an event is forward or backward actually almost is entirely encoded in the PDFs.
Right.
And in my paper, I've written an analytical treatment of how to calculate this with just the PDFs and a model. I don't know. Given that you can actually analytically calculate this, I don't know if you actually want to weight it and make it any simpler. I mean, you can, given a model, you can find out what.
I just mean how you're going to measure it, right? Not. I mean, it's okay. Just go ahead.
Okay. 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 Now the effect of this ambiguity in the initial state partons directions, is to actually dilute the forward-backward asymmetry in this frame with respect to what happened in truth. And I've tried to illustrate this by overlapping analytical curves with the CMS measurements. The dotted line here is what you would get if you knew where the quark and antiquark came from. So you can call it the center of momentum frame if you want. And this is what you would get in the Collins-Sober description, the solid line geometry. So you can already see that there are fewer forward events and more backward events, right? So that's why you get this dilution at, say, a 300 GeV invariant mass. And then as you go farther and farther, this dilution keeps decreasing. Because the more energy you put in, the more likely it is that the direction of the boost is the direction of the quark, as I should like. And then as you go really high, there's almost no difference between the actual thing that's happening in the Collins. Okay, so now hopefully we understand what we mean by the forward-backward asymmetry at a proton-proton collider. And this has been measured very well by both CMS and Atlas. Now the question is, can these measurements throw up new physics first with good significance? Okay, and to answer that question, let's try to guess what kind of new physics we can expect to see first. Okay, so let's first walk through how we usually think about finding a new particle. If this new particle was a resonance, the sequence of our thought is to first look for it in the invariant mass spectrum or some kinematic spectrum as a peak, right? Which is what you would call a direct search. And then you get at least its mass, the new particle's mass, and then you go to the angular spectra to disentangle the spin and coupling properties, etc., so that you know what UV physics this particle is, right? People have worked on this sequence for a very long time, right? And we saw this sequence in action very recently with the Higgs boson discovery also. We first discovered it in various channels as a bump, and then we go to a clean final state, like 4-lepton final state, look for all the angular distributions, and from that try to disentangle the CP properties of things, right? But if new physics happens to be a non-resonant entity, for instance, if, like I showed you, if the best way to find new physics is to look for its radiative connections to the process, or if new physics is a T-channel entity, right? Then it's not clear where to look for it first. There's no bump to look for. So which deviations become more important is, deviations in which of these two become more important is up for grabs, right? So the best strategy should be, as Marcus pointed out, for contact operators, to use all the information that you have and then at once extract the mass, spin, coupling properties, everything together. And that hopefully gives you a 5 sigma. That, I think, should be the best strategy to look for non-resonant physics. Okay. Okay, so this is the status of LHC measurements of the forward-backward asymmetry at both CMS and Atlas. And this is found to be very consistent with the standard model. So that's a good test of both standard model and new physics. And so can we use this data to constrain non-resonant entities? And to my best knowledge, this data has been lying around, at least from here, this data has been lying around for 2 years now. And no phenomenologist, to my knowledge, has used this data set to constrain any new physics, not even a Z-band. So I thought, okay, why not go and set constraints and see how good you can do. Okay. Okay. So, what is the simplest non-resonant scenario that we can think of? A tree-level T-channel exchange. Okay. I chose the T-channel particle to be a scalar. It could also be a vector. If that is the case, a T-channel amplitude interfering with the S-channel vector mediated amplitude of the channel model produces an angular spectrum that is qualitatively very different from what we have in the standard model. So can this qualitative difference be picked up in our colliders? Is the question, right? So what I've drawn here is what is nothing but a leptoquark, something that carries color and connects a quark and a lepton species at the renormalizable level, right? Okay, we have dedicated searches for leptoquarks. Can the measurement of angular spectra do better than the dedicated searches? And what are the constraints that you can get? Can these measurements kill the parameter space of this T-channel exchange? Okay, so we are now shifting a little bit into Leptoquark land, and I can bet that most of you here have not worked on Leptoquarks. It's the neglected orphan child of particle physics, just because Leptoquarks do not stand in as ready solutions to topical problems.
Well, they were the DAISY people, of course. They were the people at DAISY.
DAISY, yeah.
So.
Right. Nevertheless, there are motivations given in the literature for their existence. They appear easily as the low energy, the infrared relics of guts. They appear in technical and composite models. The Downs quark in R parity violating supersymmetry of the R parity violating operator happens to be a leptoquark. I've seen some people work on leptoquarks using them as mediators for dark matter standard model interactions. And of course, every time there's a low energy flavor physics anomaly, somebody immediately writes a leptoquark paper connecting the requisite quark and the lepton. And the motivation that drove me to do this project was the sixth one, which is that if we are going to look for new physics at the LHC, we might as well look for a species that are, so to speak, most visible. And one way to think of most visible is to make a list of species that have renormalizable interactions with the standard model formulas, and that happens to be a very small list. And Leptoquarks happens to be one of those particles that you can very easily look for at the LHC, right? Just because they have a color collider. And they might be sitting around at the TeV scale and can be easily visible. Okay. Okay. So let's get down to business. There's a huge list of leptoquarks that you can write down depending on the quantum numbers that you choose. But I'm going to be focusing on scalar leptoquark species that do not violate baryon number, and so there are no proton decay constraints on these two species. So let's take that. And you write down the model for those. And because this is a phenomenological study, I'm going to make a choice of the flavor texture of these leptoquarks, such that in one species I connect only the up quark and the electron, or just the up quark and the muon, and in the other species I'm able to connect only the down quark and the electron and the down quark and the muon. And I'm just going to name them using the same prefix and suffix of lepto and quark. So I'm just going to name them electro, mu up, electro down, and mu down, so that I know it clearly exactly what model I'm dealing with. Okay, and this is the parameter space that I'm going to probe for each of the 4 models that I told you. which is basically the Yukawa coupling of the leptoquark with the fermions and the mass. Okay, and for this talk, as an illustrative choice, I'm going to show you constraints on the electro-up model. And what I'm going to do is to show constraints that already exist from dedicated searches and other indirect searches, and show you how dilepton production can, or where does dilepton production stand with respect to these other probes. Okay, so let's begin with what we already know, which is leptoquarks are being searched for by pair producing at the LHC because they're colored. It's just like squark production, except the leptoquarks here decay instead of to jets, they decay to a lepton and a jet. So two leptons and 2 jets would be the final state that you'll be searching for. Because we introduced a Yukawa, you might have to introduce this diagram also. I'm not going to go into the details of what I did to recast. I'll be happy to talk about it offline. But you can basically take those searches and recast them into the parameter space that I showed you. And this is the region that's excluded. Roughly about a TeV is where, roughly below a TeV is excluded by the pair production searches. As you go to higher Yukawas, of course, the curve turns down a little bit because this process becomes, this mode becomes more important. Okay. But there's a second way to look for it directly, which there's only a CMS search for this, there's no Atlas search. They call it single production, although it's not exactly single production. Only the diagrams I've drawn with a red leptoquark are actually produced, otherwise the leptoquark stands in as a mediator. Anyway, the final state is 2 electrons and a jet. And there's a lot of intricate criteria that they put in to maximize the sensitivity of the search. What this search does mainly is to probe the Yukawa coupling as a function of mass. The previous one was almost entirely QCD, but this is a Yukawa dependent production process. So again, I recast everything carefully, I hope. And what I find is that, of course, the single production mode can reach higher masses. This is what they also found. Than pair production, and the bound is a function of the bound on the coupling is a function of the leptoquark mass. Okay. Now let's get to our probes, which is dilepton production. This is how the standard model looks like at the photonic level. And if I start interfering with a T-channel leptoquark, depending on the coupling and the mass of the leptoquark, I would get different kinds of spectra. The solid lines here are when I fix the mass to 1 TeV and then move the coupling around. Obviously, you get higher effects. And then the black lines are when I fix the mass and then move the coupling around so that its interference effects kicks in later or earlier. But they all asymptote to the same value in the spectrum. Okay. Now, this effect can be probed by looking at the dilepton resonance search spectrum, the MLL spectrum, and doing a shape analysis, basically a chi-square effect, and looking for the 95% complex level. So I recast that, and what I find already is that this is the bound which has already beaten a single production bound. And this is because dilepton production, first of all, it's a 2-body final state, as opposed to the 3-body final state of the single production. And the uncertainties are so much smaller here, as opposed to the L plus L minus plus a jet in the single production final state. Just because of the presence of the jet, you get a lot more uncertainties there. So dilepton production is already a better probe of the Yukawa couplings than single production. It's the first conclusion that we'll draw from. And now, sorry, I was not the first person to do this kind of recasting. Mark Weiss and his postdoc, Yu Zhang at Caltech, for completely different reasons. We're also looking at probing leptoquarks with this process. but they did not use the bulk of the events that were measured at the Atlas and CMS. They basically did boson statistics by looking at bins that had actually 0 events. But still, they also were able to set competitive bounds to single production.
Sorry, what do you mean they used bins with no events? They looked at very high energy bins?
Yeah. They looked at bins above 1.18, and I looked at bins above 5 energy.
So you're getting more because this shape is very broad.
Yep.
So you get better statistics.
Right, exactly. You get better statistics, exactly. Okay. Now let's look at the angular distributions.
So does that mean you're also more model dependent? Because you're getting some of this from the correlations between bins. For your model, that's fine, right?
Yeah. But I would. Oh, I see what you mean. Yeah, I think it is very model.
This is an optimized search for a specific model.
Yeah, exactly. Yeah. Absolutely. Okay. Now, if you look at the angular distributions, let's first see what the effect of this T-channel exchange is on the spectrum. This is the standard model spectrum at a mass sufficiently above the Z mass. But the moment I add in the T-channel exchange, you get all sorts of weird spectra depending on the coupling of the mass. If you look at just the solid lines, the red, black, and green, I just fix the mass again at 1 TeV and increase the coupling. The forward-backward asymmetry, in fact, changes sign as you go to higher couplings. Right? And the black lines, the black curves are again if I move the mass around. And once again, the sign of the forward-backward asymmetry is likely to change. So you get pretty dramatic effects by adding a T-channel exchange. As you go to higher masses, of course, the effect moves around. But yeah, at every invariant mass, you get pretty dramatic effects. And that is seen again in the, if you plot the forward-backward asymmetry itself, everything moves around. It's a huge deviation. Okay, so now let's recast the CMS measurement. And I chose CMS over Atlas because they also bin their events in terms of the absolute rapidity, which is defined as this. And so you get a lot more bins. So taking all those bins and doing another chi-square fit, Pearson chi-square statistic, you get a bound that actually slightly beats the Dilepton invariant mass bound. Right? So dramatic effects lead to very strong clusters. Okay, now this would have been a happy story because at colliders, Dilepton seems to do better than the dedicated searches. But it so happens that the measurement of atomic parity violation at low energies made in 1997, I guess, at Boulder, at Gila.
Can we just go back? I guess I realized I didn't. Maybe you said it, but I'm not really. Why I should be able to understand. And this is just a stupid thought. I shouldn't have been. Why are these kinds of analyses winning at large coupling? Why is that?
Which analysis?
Well, yours, why are yours or Y's, or why are they becoming? They're beating the pair production at large coupling.
Oh, they're beating it. They're beating everywhere, right? Not just at large coupling.
Well, the line is more horizontal than it is vertical. So I'm just saying, for any given mass.
I see what you mean. Well, I don't have a good answer for that actually. I don't know why there's some deviation. You'll see these deviations in the other models also that I'm going to show.
Okay.
But I don't know why the slopes are slightly different. it could be that, so as you go to higher Y, obviously the interference effect is smaller and the new coupling square effect is larger. And I don't know where the interference effect goes down.
I guess maybe the way to ask my question is that I guess what I'm really surprised at is that the pair production line is so vertical.
Oh,
you know,
for
example, you see what I mean? It's almost independent
I see what you mean.
of the coupling,
right?
Right. Whereas, I mean, it's clear that your effect will turn on with large couplings. So I guess that's what's surprising.
So the pair production is almost vertical because it's almost entirely QCD. Even if I had shut off the even if I had shut off the Yukawa couplings.
Sorry.
Yeah.
It makes sense. Thank you.
Yeah. Okay. These three processes are coupling, the Yukawa dependent, but this is entirely QCD. And then higher Yukawas, the pair production actually starts.
Thank you.
Yeah. Okay. So there is a 1997 measurement made at Gila Boulder with a 0.35% precision, I think. So it's one of the most precise experiments done to measure parity violation at any energy scale. And it so happens that, the precision of that measurement constrains parity violating physics such as leptoquarks. And you can calculate the deviation to the parity violating operators at low energy in terms of the coupling and the mass. And recast a 2 sigma limit, and that actually kills a lot more parameter space than any of these collider searches. A fact that is not very much appreciated in collider search literature. Neither in the HERA papers nor in the CMS papers is the atomic parity violation which I mentioned.
Was there some history about this atomic parity violation that it wasn't agreeing with the standard model?
Right.
Then it agreed, and then people stopped working on it.
Exactly.
In a very cynical way, but you see what I'm asking.
Yeah. It had a 1.5 sigma deviation from the standard model.
It was only at that level of 1.5
Yeah.
sigma.
Yeah.
And then, but then it went. Now it's how close is it to the standard model?
Now actually we can calculate from this. I don't, but I just remember that. The latest calculation.
Oh, sorry, there it is.
I'm sorry, I think the latest calculation gives a 1.5 sigma deviation.
The latest one, yeah.
Yeah.
My memory, I mean, this was in the 80s. I was still alive in the 80s. It was, I thought it was a bigger deviation.
It was 3 or something.
3 sigma. So, I don't know. I mean, okay. And this is the last word on it, the subject, 1997.
Yeah.
All right.
Yeah, the last word on the measurement was 1997. The last word on how much deviation came like 10 years ago. Some theory group made the standard model calculation and found the 1.5 sigma.
Okay.
Yeah. Actually, to be honest, I still haven't figured out what exactly the experiment measured. What you can extract from that measurement is the nuclear weak charge, and from that because that's easier to connect with the standard model Lagrangians that we know. But I don't know exactly what they measure. And
there's some nuclear physics in there.
Yeah.
Probably shouldn't believe them.
0.35% accuracy. Okay, so yeah, that cuts out a lot more parameter space than the direct and indirect collider searches. But that is if you have a connection to electrons. If you looked at the other flavor structure that I was talking about, which is connecting an up quark and the muon, then of course there are no measurements made in muonic systems for parity violation, and the dilepton searches do better than the single production searches. Now let's look at all the 4 models. This is when you connect the down on the electron and the down on the muon. Every time the electron is interacting through a leptoquark, atomic parity violation wins. Otherwise, the dilepton production does much better. So at colliders, dileptons are the best probe of leptoquarks.
You didn't do taus?
I deliberately didn't do taus. Yeah, that's one reason is they have a m-tau, they have a invariant mass measurement, but not an angular measurement. So I couldn't make a nice apple taus. Okay, but will this bad news stay bad news? Can we ever do better than atomic parity violation at the LHC?
But it still might be worth doing. I mean, because I think one of the messages here is that, you know, these are even just collider searches, right?
Yep.
You're winning
Yeah.
large couplings, so.
Yeah.
Even
I definitely.
The invariant mass, it looks like there's a lot of information in the rates. Right?
Right. Absolutely. Yeah. Yeah. Yeah, and I believe the tau measurement should do a lot better than the single production when you have the tau in the final state, because here you're going to have tau jet in the single production final state, and that has almost like 3 jets in the final state, right, when you have hadronic tau decays. So I believe that it's going to do much better. Okay, can the LHC ever deliver enough luminosity and so enough precision in this channel to overtake the 1997 standard bearer of precision? Okay, and I find that the good news is yes, in fact quite easily. If we were to hit the design luminosities of 300 and 300 inverse interval and 3 inverse attogon, the dilepton probes do much better than the atomic parity violation probes. Here in this plot, the red lines are looking at the MLL spectra, and the green lines are forward-backward asymmetries, and the dotted lines is when you have 300 inverse interval, and of course these are the 3 inverse attogon luminosity, the solid lines.
Why is it only like a factor of 2 for 10 times the luminosity? That would be more like a factor. Or is it a factor of 3? It should be like a factor of 3.
Because it's the couplings.
Yeah.
No, it's coupling
so
to the 4.
It is square root 10. It's basically that. Right? It doesn't look like it. But
Isn't it coupling to the 4th?
You're right, it's coupling to the 4. I'm sorry, it's coupling to the 4. So yeah, so that's why you're not going to say.
Yeah.
Okay.
Okay, so that's one kind of forecast. The other is, well, I don't know if we should spend time on this, but if, as we go to higher and higher masses and don't see leptoquarks, we're also accessing higher and higher couplings, and then from my experience working with these dark matter loop diagrams, the threshold effects from radiative corrections should start kicking in, and I think that will have interesting effects on the spectrum produced by leptoquarks. But that's for another day. Okay, now if we were to start seeing funny things in dilepton spectra, to me at least things will get doubly interesting, because first of all you can start testing its leptoquark origins, but also using angular spectra you can right away start telling what the spin of a leptoquark is, which the angular distributions clearly mark out. Okay. And this is a plug. I'm also doing a project with a student in Notre Dame and my bosses, Antonio and Aaron, looking to pin down the fundamental properties of dark matter, what its spin is, what kind of chirality structure it has for its couplings with the standard model. Do you have good sensitivity, etc., by looking at the angular spectrum of dileptons in these kinds of models. So that's another non-resonant scenario that you can start looking for in angular dilepton spectrum. Okay. How much time do we have? Okay.
We started late, so go.
Sure. All right. So that's the physics part of my talk. I also wanted to advocate my personal view on how angular distributions should be presented in the future, in the LHC era at least. Okay, so that things are really clear, because I started wondering why people have not actually jumped on the angular distributions, although you have clean measurements, etc., etc. And I think there's a psychological difficulty in the way we interpret these plots, the forward-backward plots, for example. So let's look at what we mean by the angular forward-backward asymmetry in an E plus E minus collider versus hadron collider. Okay. Now, in an E plus E minus collider, the forward-backward asymmetry is a Lorentz invariant quantity, at least as far as boosts in the logical direction are concerned. Okay. But in a hadron collider, you are not sure where the quark and antiquark came from, so you have to pick a special frame, which is the Collins-Soper frame, and so it is not a Lorentz invariant quantity, which you can see easily by looking at what goes into these equations. Here, it's the difference in the rapidities, which is invariant under boosts. Here, it's the difference in the absolute value of the rapidity, which is not invariant under boosts, right?
I'm sorry, I have to
Yeah,
leave it
okay.
because I'm now
Sure.
walking out and discuss.
Yeah, no, of course. See you. And let's also look at the history of this AFB. The AFB, as far as the Z discovery is concerned, was a pretty useful variable because it was 0 to begin with when we had just the photon mediated process. And then we started seeing interference effects of the Z by catching on to a non-zero forward-backward asymmetry. So we knew something was going on there. So going from 0 to non-zero makes new physics so much more conspicuous, right? But now in the standard model, we know that at high invariant masses, which is where we are trying to make discoveries, the forward-backward asymmetry is not 0. It's fixed to some flat quantity. And so in light of this, it would be nice for new physics interpretations for a phenomenologist, if we can characterize angular distributions not as forward-backward asymmetries, not as the traditional variable, but something new, which is both Lorentz invariant and something that vanishes in the standard model. Lorentz invariance is important because if you can use only Lorentz invariant quantities, analytical calculation of the spectra becomes very easy, because there's a direct relation between the delta y here and cos theta that you can write in the center of momentum frame. And for a theorist, calculating things in the center of momentum frame is so much easier than putting in Parton distribution functions and convolving them in funny ways, etc., etc. It's not obvious how to do it in other frames, right? So let's see if we can satisfy the first criterion. Of course we can. It's the difference in the rapidities, and if you just take the absolute value of that difference, then we are done. There's no sign ambiguity anymore. We don't care which direction the quark and antiquark came from. This is something that's already being done to characterize the jet angular distributions that are measured at CMS and Atlas. So they just dress it up with an exponential and they give you distributions in this variable, chi. Right? So we could start by doing something like this so that we theorists who want to interpret beyond the standard model, etc., etc., can make rapid calculations in the center of momentum frame and then just match their plots to the measured values. Can you also find something that vanishes, so that if you measure a non-zero value, a new physics interpretation is immediate? One potential quantity that can do this is what is called the center edge asymmetry. These authors advocated it in their paper. And this is nothing but looking at the angular spectrum, picking out a central region that contains roughly half the population of the events, and then subtracting the events on the outer edges. Okay, and if you can find a y0, which is the central boundary line, such that the number of events in the center are the same as the number of events on the outside, then this quantity goes to 0 at some perturbative value, of course. Because NLO effects can always reshape the angular spectra slightly, but you can always find a place where this happens, right? Then it's so much easier then for a theorist to calculate this, because cos theta is what we calculate in the center of momentum frame. It's defined in the center of momentum frame. So we just take the absolute value of that, and that turns out to be nothing but this quantity in terms of the difference in the rapidities. And it doesn't matter what frame you are in. If you take the area under this curve in the center and subtract it from outside, it's going to be the same. Okay? So it's completely frame independent. And I've tried to show the usefulness of this quantity by illustrating this with leptoquarks. If you choose cos theta to be a certain value, the standard model central edge asymmetry vanishes, and then you should be able to see Leptoquark signals with this. But even cooler is if we see something funny in the Dilepton distributions, if we use this quantity to interpret it as a Leptoquark, then we can immediately tell what the spin of the Leptoquark is, because the spin 0 Leptoquark will always produce a positive center edge asymmetry, and the spin 1 will always produce a negative center edge asymmetry. So, yeah, I thought that was pretty neat. Okay, that should conclude my talk. The take-home message is angular distributions, not just in this final state, even in the jet final state, dijet final state, is largely ignored by the phenomenology community, but can be a rich probing ground for non-resonant physics. There's so many non-resonant models that we can write down that may first turn up in angular distributions. And of course, the forward-backward asymmetry measurements and the MLL spectrum measurements give much better limits on the Yukawa couplings than the dedicated searches at the LHC for Leptoquarks. And it would be nice if there's a clean interface between experimental presentation and theoretical calculation by the use of spectrum characterizing variables that vanish in the standard model and are Lorentz invariant. That concludes the talk.